Let me start recording now. All right, so a little bit background about myself. I finished my graduation in 2002 from IIT Roorkee. I worked with a company called DE Shaw, and there we built big data systems even before we started calling it big data system. Okay, we built systems capable of hundreds of terabytes of data in 2002. Okay, so DSHA has been a very sort of a pioneer when it comes to handling a lot of data. After that, I started a company called Tbits Global, where we built a document management system on the lines of what you have MongoDB, sort of similar to MongoDB. And after that, I joined a company called InMobi, where we built a recommendation engine churning close to 200 terabyte data. After that, I joined Amazon and built a high throughput system for their Amazon.com website. Using and we used some in-house NoSQL, and the design was similar to what we have Apache Storm in the public. All right, so that's and afterwards, last year in April, maybe my first training started in August, I think. So we started No Big Data that time. All right. So let me go through the introductions. Let me go through the introductions, and yeah, I think we need to do something about my name, but that's all right. Okay. So is my voice clearly audible to everyone? Am I audible to clearly? So Jairam is saying that there is some noise. I'm hoping that it should finish. All right. Is anybody else hearing the noise as he's complaining? All right, all right. So Jairam, it's only you probably. Uh, yeah, because everybody else is saying the voice is fairly clear. All right, great. So today we are going to discuss something called what is big data, why are we talking about it now, and then we will go into Hadoop architecture, and we'll go into the details of HDFS. So this session is going to be half generic and half little esoteric. So, I mean, this will give you a clear understanding of what exactly is big data and what is Hadoop. All right. So, let me go through your introduction. So, we have Siddharth. Okay, and all right. And we have Ravinder. Ravinder is a delivery head at HCL Technology. Welcome, Ravinder. And we have Kajari in the session, and we have Pavan. Pavan is a business analyst at with Citigroup. Uh, okay, welcome Pavan to the session. I'm sure uh, you will like the session. We have Santana from Ambience, and he's working at experiencing in mobile application development and in new to big data. All right, so okay, welcome Rajesh. Welcome to the session. We have Siddharth, who is a business analyst at Target Corporation. Great, Siddharth. We have had candidates from Target already, and welcome again. And we have Nitesh, who is a equity research, okay, who is into equity research, and Siddharth is into risk and fraud analytics. Great. Naveen is a channel sales leader at IBM Cloud and Mobile First. Excellent, excellent. So IBM is our knowledge partner, by the way. And Nitesh is also new to big data. We have Sarju. Sarju Gurung is a systems engineer at Qualcomm. Great, great. So this is the session one. This is session one of our 11 sessions. And Jairam is working as test lead at TCS. Great. All right. So let's start with a very simple question. What do you understand by big data? Okay. So let me ask you first that what do you understand by big data? All right. What is it that you understand by big data? Okay, Siddharth says big data has the following property: volume, velocity, veracity, and Sarju says complex data with different format, which is growing over the time. Rajesh says large volume of data available with variety and which cannot be computed with conventional hardware. And Siddharth says mostly unstructured. Okay. Anybody else? What do you understand by big data? Yes. All right. All right. So yeah. So Setu, you will only hear my voice. I will be repeating everybody's what others are writing because nobody else is speaking. Okay, everybody else is muted. All right. So there are a lot of definitions of big data, but we will stick to a very simple definition that big data is something which requires distributed architecture. What does it mean by distributed architecture? Distributed architecture means something that a software that runs on multiple computers at the same time. So the data which is quite huge, or your problem which is quite difficult, or your problem which requires churning the big data, if for solving your problem you require your software to run on multiple computers, then you say that you are handling big data. Okay, that is a simple thumb rule. That's a simple thumb rule, and we will stick with this thumb rule because every other definition of big data is humongously confusing. Okay, so we'll just stick with this definition. A distributed architecture means a software, an architecture that runs on multiple computers simultaneously to deliver the output is called a distributed architecture system, right? So, okay, so data of very big size. Big data generally means data of very big size. Okay, let's not confuse big data with big data analytics, big data problems, and big data does not solve any problem. It is the big data analytics or big data solutions that solve your problem. Big data is a problem in itself. All right. So big data is data of very big size that you cannot process with your usual single computer systems, and you require distributed architecture. And this data can be of any form, whether structured or unstructured. Structured means that in the input, in the data you know that these are the fields and these are the data types of the fields. That kind of data is called structured data. Example is your data in MS SQL. While unstructured data is something you do not know the fields in the input. You don't know their data types, you don't know the fields. You only know that there is this text or there is this binary which contains the data. To convert an unstructured data to structured data, you need parsing and you need to identify the format of the data. Okay. Now there's something called semi-structured data. Semi-structured data is something we know the format of the input or we know the format of the data, but we do not know the data type of each field. We know that our input data contains these fields, but we do not know what are the what are the data types of each field. That kind of data is known as semi-structured data. All right. So hope that this definition, I'm not going with the IBM's way of defining things. I'm going with the practical way of defining big data. That will that will make you very clear about how to say that this is big data, this is small data. All right. Now, because more than why do we need to define that this is big data, this is not big data, so that you can do the selection of tools accordingly. If you realize that this is the kind of data which you cannot handle on the existing systems, then you can go on to use any of the big data tools. All right, we'll go into the identification of that kind of systems. Once you have an idea that when you're churning some data, it is going to take these many hours on a single computer, no matter what optimizations you do, then you will automatically realize that you need to move on to big data systems. Okay, but before that, it is important for you to know what are the various components in the big data solutions as of today. Okay, so this first session should be a very good introduction for all of you and should give you a fair amount of knowledge so that you can decide further. You can decide further which course do you want to take, or you need a course or you don't need a course. All right. Now, Jayaprakash point is big data is a process of changing data into information, which then changes into knowledge. No, big data is okay. I'm being little, why? Being little upfront. So, big data is just a data which is huge. It's not a process. Okay. Big data solution, it might be a solution, but big data is you know it's a data. It's a noun, and big is an adjective. It's not a verb. Okay, it's not a process. Okay, what you have defined as a process is conversion of data into information, which then changes into knowledge. So this is the whole big data solution what you have described. All right, so let's not confuse big data and big data solution, because that is something which we will have to tackle. All right, so this is the definition which will stick to while trying to solve the problems. Okay, now this is the definition which people might ask when people ask you in the in the formal way. This is the definition you might like to give, but this definition may not take you anywhere. Good. So Amit's question is, how big is the data size to qualify it as big data? We will talk about it, and I'm hoping that you should be able to answer it. All right. So again, this is a formal definition where we say that a data can have these four characteristics that might make it big data. Okay, and again, big data, for the qualification of the big data, is something that requires distributed architecture. Okay, and these are the characteristics. These four characteristics are the characteristics which might push you to to change your problem definition just because your data turns out to be big data. Okay, now let's have a look. What are these four characteristics? These four characteristics are very generic characteristics. Okay, we all know that data has volume, meaning we all have been talking since uh, last 20 years about gigabytes, terabytes of the storage. So that storage is the volume. So first characteristic of any data, not only big data, any data, it's the volume. Second characteristic of the data is velocity, meaning at what rate are we accumulating the data, or at what rate are we transmitting the data, that is the velocity. Third, in what format is our data, whether it's map, whether it's you know so your data would not necessarily be only in the form of relational. Your data could be in the form of videos, your data could be in the form of audio, it could be Google Maps, it could be geographical data, it could be anything. And every data need to be churned. Okay. So the volume characteristic, when the data grows huge, there is a stage when you realize that it makes no sense to store this data on a single computer. We need multiple computers to store this data. That's when we say that because of the volume, our data has become big data. All right. As you can see that Facebook stores 50 terabytes additional data every day. Velocity. There could be a scenario where your data is coming very fast, and to handle that kind of number of requests per second, we might have to have multiple systems. Imagine this. You have a solution, a very simple solution, which basically counts the number of hits on a website. Okay? All it does is it increases a number saying these many people have visited the website so far. These many people have visited your website so far, right? Which means although the the overall accumulation of the data is almost negligible, it's just one big integer which says that these many people visited your website. Now imagine the same counter being used by hundreds of people, say 200 people, and these 200 websites these 200 websites who are using this counter are fairly busy. Lots of people visit these websites. Now, at the end of day, it's only the 200 integers which is being accumulated every day, right? 200 counters. These are the hit counters of these websites, right? So the accumulated data is very small, but number of requests that would be coming to these website, if you sum up all those, will be too high to be handled by a single computer, right? So for this website counter, you might have to put more computers in place so that it can handle so many requests per second. And that is what is known as velocity. So by virtue of the velocity, you ended up having, by virtue of the velocity, you ended up having too many uh, multiple computers. You ended up having a distributed system. And that's when you say that velocity means velocity made your data bigger. Okay. Third is variety. Even if there are situations when, even though your data is smaller, even though your data is not moving, still, just because of the format of the data you are processing, you might have to use a distributed architecture. You might have to use multiple computers to solve your problem. And that's when you say that it's by virtue of the velocity we have big data, right? Let's take a case of Google Maps, right? Imagine Google Maps of a country. The total Google Maps would be, say, 300 gigabytes for a country, or maybe 400 gigabytes. So 400 gigabyte is not too much of a data. Okay, 400 gigabytes is not too much of data. But and this data doesn't have velocity. Now, but if you have to the find the way from one location to another location for a country, you might have to use a distributed architecture just because it is a little complex task, and your single computer will be fairly slow. Therefore, you might have to use multiple computers to solve your problem, right? So that's where the variety plays a role in making your data big. Fourth one is the veracity. The fourth one is veracity. Veracity is just because of doubt, just because of doubt in the data, we ended up having multiple data sets. And basically, because of the veracity, we ended up having too much of volume or too much of velocity, and hence it ended up becoming big data. All right. So is it clear to everyone? Any questions here? No questions? Great, great. So no questions, that could mean two things. One, I did not explain anything. Second, I explained really good. I believe that it's the first one. Okay. So let me explain velocity once more. S- Okay. So Japraka's point is, then can you explain velocity once more? Velocity is when you have too many requests coming per second. Okay. So you can think of volume when you think in terms of Facebook. Imagine that how many people would be asking for their feed every second. every second there are millions of users who are sending requests to Facebook to get the real update of their feed. Okay, every time they refresh their feed, there's a request goes to the Facebook automatically also. Now imagine total number of requests that are reaching Facebook. Okay, and these requests are too high to be handled by a single computer, and this is what is known as velocity. Okay, the other example of velocity could be a session like today's, what we are talking right now. Even though there is no data accumulation, I'm talking here, there are hundreds of people in this session. If there are hundreds of people in this session, so my voice per second is being multiplied by 100 and being distributed to all the people. So this is a lot of data in the motion. All right, now we have Rajesh's question. Conventional data warehouses are big enough and are stored in RAIDs. Okay. Now we will talk about it. So conventional RAIDs do not generally qualify for distributed architecture. Okay. Conventional RAIDs do not qualify for distributed architecture. A third is, even if we are able to handle volume, even if we are able to store 1 terabyte of data, if a computer has to read 1 terabyte data, if a hard disk has to read 1 terabyte of data from, I mean, if you have to read 1 terabyte of data from a hard disk, it will take close to 5.8 hours to just read the data continuously. Okay, therefore, even if you are able to store it properly, most of these systems give you really bad performance. Okay, and therefore is not really considered a great solution when we talk about handling huge big data. All right, so Rajesh, was I able to explain? So Santana's question is, why are these parameters coined in the words of V? It's generally, alliteration, figure of speech. And those consultants at IBM who coined these definition really had this, urge to make itself popular, and that's why these are all starting with V's. Uh, all right, Santana. So, so they keep on adding one more V every year. I'm talking about IBM per se. They keep on adding one more V. This time they've added something called value into the definition, but the definition has no limit. Okay, they might add a whole dictionary starting with V and still they could make some sort of sense. But the truth is, the way with a big data is defined is it is any system which qualifies for distributed architecture, or any data which requires a distributed architecture is classified as big data. Okay, any data or any churning of the data that requires distributed architecture, in those situation we call that our problem is big data problem. So we have Srikanth who just joined, and he's working for HP on ETL tool Informatica. Good, good. So we have had people from ETL background, so no worries. So far you have missed nothing except for the definition of big data. Big data means any data that requires a distributed architecture. Okay. All right, so we simply tried to convey only one thing so far. Big data means distributed architecture. Any data or any problem which requires a distributed architecture. All right, now let me ask you very quickly, how many bytes are there in a petabyte? Anybody? First answer, and I'll move. All right, it's 10 to the power 15, not 12. 12 is terabyte, not petabyte. All right, yes. So it's close to this. Those people who have searched on Google, they would answer this one. All right. The general way of remembering it is in this form. 1 kilo is 1024 bytes. 1 mega is 1024 kilobytes. 1 giga is 1024 megabytes, and so on. Okay. So this is how it is. Now the next point is the most important question. Do you think 1 petabyte data is big data? If your problem involves handling of 1 petabyte data, is your problem big data problem? Okay, Ravinder says no, Rajesh says yes. Anybody else? Siddharth says yes. Kazri says, I think it is decided by the capacity of my hardware. So probably you should have a rough idea. You should always have a back of the envelope idea on what kind of hardware is generally available. Malay says yes. Siddharth says if 1 terabyte requires 5 hours, it's not 5 hours, it's 5.8 hours, which is close to 6 hours. If 1 terabyte requires 6 hours only to read, then it is a big data. I think that's, yeah. All right. Now, Sarju says reading of 1 terabyte of data is a big data problem. That's correct. Even the storage of 1 petabyte data is itself. Here we are talking about 1 petabyte data. Okay. Santana's question is if my computing system is not capable of handling 1 petabyte, then it's a big data. Right. You should know your computing system or a general computing system available as of today. Rajesh's question is if we compare today's data volume, then it is big data. Few years down the line, it will be a normal data. That is correct. So Siddharth says petabyte is big data. Right. Sarju says cause it requires sorting and reading. Excellent. Great. Great set of answers. Anybody else? Good. So yes, most of the existing systems cannot handle 1 petabyte data in a reasonable amount of time. Now you can imagine this. Even if you build a hard disk having 1 petabyte data on top of another, reading this kind of data would require how much? 1024 into 6. This is 6,000 hours will be required just to read this data from the disk. 6,000 hours. All right. So close to a year it will take. All right. So you should answer to me in this session, not to Anjana or anybody. Okay. All right. If 1 petabyte data is structured data, say in RDMS, does it have big data problems? Yes, it is. Amit's question is very good. His question is, I'll repeat for all. If 1 petabyte data is structured data, say it in RDBMS, does it still have big data problems? The answer is yes. At the end of day, every hardware is storing it in the disk. Okay. Now, storing 1 petabyte data on a single computer in itself is almost difficult thing. You will have to either build your own custom big data solution or you will have to utilize existing ones. All right. You will require multiple systems to actually store 1 petabyte data properly, right? Whether it is structured or unstructured. Anybody else? Good, good. So we are all clear and thorough with the definition of big data. Okay, probably that is one thing which I found lots of people to be confused about. All right. So now this is the general graph which everybody has been talking for quite some time. The data has exploded, the digital data has exploded exponentially. It has increased exponentially after year 2002. This graph shows that the upper part is an analog storage, such as the paper, the film, the audio tape, the vinyl, and all that. The lower part is the digital storage. Digital storage is in DVD, Blu-ray, hard disk, and flash drives, and whatnot. There was a point in time in 2002 after which suddenly the data started growing, the people started buying the flash drive and all of this at an exponentially increasing rate. Okay, so what exactly happened that time? What exactly happened here which caused this kind of expansion? The answer is twofold: hardware and connectivity. Hardware and connectivity. The hardware became cheaper, faster, and smaller. Cheaper, fast, and smaller. These are the three criteria of any hardware manufacturer. And in 2002, the mobile phone became available. Mobile phone is an example of a computer where it has become cheaper, faster, and smaller to a very high level. Also, the connectivity became quite commonplace. People started having Wi-Fi's, people started having broadband connections. It became connectivity also became faster and it became cheaper. All right. So while the hardware generates the data, connectivity coupled with the software multiplies the data and transmits the data. The connectivity makes the data available to all sorts of people. Okay. Therefore, both of these things, when you combine, it gave this kind of a graph where data grew exponentially. Okay. Take a case of this session. I will be creating I will be creating close to 2 GB data during this session and it will be uploaded from me to GoToMeeting. But if there are 100 people in this session, those the data is going to be multiplied by 100, which means 200 gigabytes of data is going to get transmitted. Therefore, connectivity multiplies the data while hardware creates the data. All right. So moving on. Now we've established that what is big data. We established that what kind of data we call big data. And we also established why the data has generated so fast. And now, why is big data a problem? Why do we need to worry about it? Why are we having this session today to discuss big data? Why do we require special treatment about it? Okay. So let's first understand what are the various components do we consider when we think about big data and its the computing pillars. All right. So there are four basic components which when we do computing, we we count these four basic things. First one is CPU. CPU is undoubtedly the most important part of the game. If your CPU is not there, nothing will make any sense. Okay, nothing will make any sense. And a CPU means it reads the things from RAM. It reads instructions, the data from various places, and take a decision on what need to be done. Okay, CPU is nothing but a complex circuitry which can understand the instructions and take a decision. Interestingly, CPU is rarely the bottleneck in most of your problems. In most of your problems, you will be surprised that CPU is hardly the bottleneck. There are other factors that become the bottleneck. The most prominent of all is RAM. RAM is the random access memory from which the CPU reads the data. RAM is extremely fast, but is fairly small storage device. And the other problem with the RAM is if there's no power, nothing is retained in the RAM. RAM is basically another electronic circuit which the maintain the state by virtue of various kinds of mechanisms such as polarization. I mean there's a what do you call, there's a specific circuit we call it, and so RAM is r- really fast, right? So, and when I talk about RAM, let's think about RAM as L1 cache, L2 cache, and all of that cache. So, the interesting part about RAM is generally it is the RAM which is the bottleneck. So, even if we keep on increasing the CPU, it wouldn't make your computation would not become really faster. Right. Now, third part is the disk size and disk speed. Disk size is generally not a problem, but disk speed is the problem. Normal hard disk, what we have been tackling so far, were fairly huge. We could store a lot of data in those, but the speed is fairly slow. As a thumb rule, it takes 20 seconds minimum to read 1 gigabytes of data from a normal hard disk. Okay, solid state hard disk is around 20 times faster than the normal hard disk, which means if you read 1 gigabyte from a solid state drive, it will take 1 second. All right. So the thing is, in case of a disk, it is the speed which becomes the bottleneck. If you are talking about 1 terabyte data, sounds really easy to say 1 terabyte because it just costs 4,000 rupees to buy a 1 terabyte disk space. But when you want to store or read 1 terabyte of data, is horribly slow. It will take 6 hours just to read 1 terabyte data from the disk. Okay, so disk is another bottleneck, and disk is also required because you cannot keep your all of your data into RAM. Reason being, RAM is generally very costly, very small, and RAM is also RAM cannot retain the data if there's a power shutdown. So you have to have the disk, good enough disk. But after a point of time, when the data keeps on increasing, the disk will also get full, and you need to have more disks, right? And so on. And after a point of time, you might have to have different computers to store this data. And that's when the network comes into play. If your network is slow, then nothing works. Because when we talk about volume velocity, everywhere the network counts a lot. All right, and therefore the strategies which we stitch when we are handling a lot of data is we transmit less data over the network. Instead, we transmit the code to the data. So these are the four precious resources of a computer which matter. And when we are tackling big data, at least one of these will become the bottleneck. At least one of these will become the bottleneck when you will realize that hey, it will be better that we buy more computers and then share the load. And to share the load, you will require a big data solution. Okay. So are we all on the same page? Any questions on this? So at least one of these components will become the bottleneck. At least one component. All right. Now let's take a few case studies. Who who are the people who store this kind of data, petabytes of data, and what do they do about it? Okay. The thing is, almost all of, even if our companies are smaller, we can come up with big data solution or big data problem which we want to solve. It's only up to us. Okay, but still I'll take few case studies so that we all understand what is the utility of such kind of systems. All right, because when we look at this kind of problems, we say that it's too much of a hassle. Why are we even bothering about handling this kind of data? All right, there are few use cases which are very popular. One is e-commerce. Out of e-commerce, the most important one which you all can correlate is the recommendation system. A recommendation system is something which takes the historical data, and based on that historical data, it generates the recommendation. It generates that these are the things which user might like. So these screenshots are from Amazon.com, where it shows that customer who bought this item also bought this. This is a product to product recommendation, where based on a product we have no history of the user, still we are giving recommendation. Then there is another recommendation which is people generally wear this product with these things. Okay, that is another form of recommendation. Then there is another form of recommendation in form of movies. Based on your historical habit, your historical information that you watched this movie, you like this movie this much, and hence these are the movies that can be recommended to you. All right. So this is what is known as a recommender system. Recommendation system is fairly old system, and in recommendation system, companies like Amazon found that it's the recommendation system which made their sales happen most. Lots of people actually bought things just because of recommendations. All right. Even in the emails, they send the recommendation, and that converts people, that convinces people to buy things. All right. So a recommendation system is something which found the use case eh, very early in case of big data. Now you might say that what's the point of big data? We understand that recommendation is useful, but what's the point of big data in this? So Amazon realized that the bigger the data, the better the results. If you have very small data, say you are trying to churn last 2 weeks data, the results you will give will be very fairly immature, very immature, and therefore you need to churn as much as data as possible to give the best possible recommendation so that people can trust your recommendation. They will try your recommendation once, and then once they have a fair amount of trust on your recommendation, then your recommendation will actually start to contribute a lot. All right. Now let me just show you in a very glimpse. This is a fairly technical thing where if you have to build a recommendation in next 10 minutes, what are the things you're going to do? First, you prepare user ID, product ID, and the rating given by this user to this product. You form this big Excel sheet kind of 3 columns Excel sheet kind of data, and then you feed that to Mahat's recommender. We call it collaborative filter, and it will automatically give you the recommendations. That's it. It's as simple as that. Okay. So this is how 99% of the recommendations is done in the industry. All right. So all you need to do is form this kind of data that this user like this product and this much, and then feed it to Mahat, and this will give you the results. So this is just one algorithm. There are multiple algorithms which require multiple format of data, and rest is up to you. Okay. So this is what is known as the recommendation engine. Now second part is the sentiment analysis. Is everyone with me? All right, all right. So keep asking questions. Do not wait for the for me to finish. Uh, I'll pick up the question as per my wish. But as and when you get a question, write it down rather than waiting for me to finish. All right. Okay. So another big example and popular example is the sentiment analysis. What is sentiment analysis? Figuring out the general sentiment of the people towards you. Okay, you have got a brand, say KFC, McDonald's, or anything else, and you want to see whether people are happy or sad, or what has been the impact of a recent campaign which you have launched, or you have recently launched a particular advertisement. You want to see how are people responding to your ad. Okay, so you basically tap into various kind of data from public tweets, okay, from Facebook, from Twitter, from various other sources. You try to find out the various sentences people are saying about you, and then you analyze each of these sentences, whether it's negative, positive, and then sum it up, and that summation will give you the general sentiment of people about you, whether it's negative, whether it's positive. All right. So that is what is known as a sentiment analysis. Right. So That's what is known as sentiment analysis, and that's also a fairly simple thing to do. Algorithm wise, most of these problems are fairly simple. The problem lies in transforming the data from one form to another. The thing which we had been calling ETL for ages is actually fairly difficult thing when you talk about big data. Okay, if you have got say 200 terabyte of data and the way you are transforming it requires duplication of the data, then your solution may not be efficient. Okay, so the whole ETL is actually changed when we talk about big data. For each operation with respect to the extraction, transformation, or loading, meaning ETL, you need to think through before you taking a step. Okay, all right. Now, the other use cases of big data are government for fraud detection and justice, and healthcare. Healthcare has been the biggest user of big data for past few years. Recently, Google also published a big data research where they said they basically did a lot of contribution to the drug industry by learning from the behavior, learning from the behavior of the disease towards a particular drug. Just because the data was too high, they could figure out a pattern. They could figure out patterns in it. Okay, so there is a lot of things which are going in healthcare as well, and there are many users of big data as of today. Every other organization is moving towards it. Okay, this slide shows you a lot of users of big data. Now Santana's question is the friend suggestion made in Facebook a recommendation system? Not really, not really. It's a complex thing what they have done. Although theoretically they are recommending us the friends, it's a recommender. Okay, but the kind of recommendations we were talking about, it doesn't fit into that one, those algorithms. Here it's more like a graph search where they try to find out which are the users who are not your friend but are at one distance from you. There are more than one common friend between someone and you. All right, so there are many people, many companies who are using big data as of today, small or big, small companies or large companies, right? Here are the 11 common myths about big data. First one is lots of, I keep hearing it now and then. Big data always means data above or in the range of terabytes. The answer is it depends. It depends on a simple fact. Do you require distributed architecture for the kind of data you are handling, for the kind of problem you are solving? Then your data is big data. All right. Second is, lots of people keep on saying it's about social media, it doesn't apply to me. It so appears to lots of people that it's because of social media only people have that kind of data. But if they look at it closely, it is their own habit of not storing the data. Because of their own habit of not storing the data, they don't have data. Okay, I talked about 200 terabytes at InMobi. I was churning 200 terabytes at InMobi for building the recommendation engine. Now they have launched it again, the same system. What was the 200 terabyte data? Exactly was that 200 terabyte data? It was nothing but Apache logs. The people at InMobi, who were mostly from Yahoo and Google's, they realized that if we don't store Apache logs properly, Apache logs is in website logs. Okay. So if we don't store that, if we store that kind of data properly, then we will have a lot of insights to make. And just because they were cautious enough to start storing that data properly, they were able to build this kind of brilliant recommendation system. We were able to build that kind of systems. So it's not about social media. It is about I mean about any data. The only thing is we need to keep our eyes open where all we can capture the behavior of our end users. Okay. Rajesh's question is, can you point to any website where we can learn some use cases of big data, especially in case of healthcare, and the solutions to some of the big data problems in real world? Right. So I think the best place would be the users of Hadoop. If you look at the users of the Hadoop, they generally keep on publishing this is what various companies are doing. Okay, so best place would be you go to Hortonworks. At Hortonworks website, you will see various kinds of use cases. Naveen's question is, can you please let me know the use cases for transportation and logistics industry? Yeah. So let's take a case of transportation industry. I was talking to some people in trucking industry. Okay. So what they were doing is they basically were planting a device in all these trucks so that their location could be quickly tracked and found. People can locate them and then talk to them. But if there are lots of data continuously changing every second, first you need to store that kind of data. Okay, if you have say 10,000 trucks and all of them are sending their data every second, to handle 10,000 requests from these trucks will be a huge problem, and you would require this. So for that kind of system you require a big data solution. Okay, so that's one example. There are many use cases. Okay, and there are many use cases. Probably I need to prepare different kinds of slides for that. I've not prepared. Sports analytics, there are many kind of analytics which are happening as of today. In sports, the most popular one is the video analytics. All right, so you analyze video for various kinds of general behavior of a particular team. This team hits to this direction these many times in past 20 years, or this player's behavior for past 10 years has been like this. Based on that, a lot of analytics actually happens. Yes, so what Naveen is pointing to is that Major League Baseball one. Okay, yeah, that's exactly that it was used. So there are lots, that is just one use case which became public. There are many such use cases that have happened at these industries. All right. Now, third one is a common myth is that big data will replace EDW, enterprise data warehousing. My quick answer is no. It will not replace the EDW. Reason being, enterprise data warehouses is really brilliant when it comes to consistency and transactions. All right. That kind of transaction consistency is not provided by any of the existing big data solutions. All right. So for the data which you require a consistency, and transactions. You might like to continue using ETWs, while for the data which requires high throughput, high storage, and high variety, you might use a big data solution. All right. Fourth is it's just a buzzword, no practical application. There are many practical applications of big data. It's not no longer a buzzword. It's a new concept. It's not a new concept. It's just the old concept, but new keyword. As I was talking to you about my experience is at DSHA, where we had been handling and building these kind of distributed architecture solution for quite some time. So it's not a new concept. It just became public recently. Sixth is it will be the future. No, it is the present. Seventh is expensive. No. Reason being, most of these solutions are open source. Everything is open. Their documentation, their installation, everything is open, which means that there are companies like mine who give you the training at really cheap cost. While if you go through the SAP trainings and other trainings, you will realize that they are charging a little too high just because they are not open source. Okay, they are not open. Next myth is it's only for data scientists. No, it's not only for data scientists. Data scientist is just one user of it. Nine, we have enough hardware, don't need it anymore. This is a very common excuse I get. So big data is not about hardware, okay? It's about this architecture where you utilize your existing hardware to solve the problems which cannot be solved on isolated systems. We will build it when we need it. That's another common excuse which I hear it. The problem with this psyche is you will not have the data when you need it because you did not build it when you wanted to store the data. Okay. Later point of time, 5 years down the line, a company realizes that, oh, if we had this much of data, then we could have analyzed this much of behavior. Therefore, you should start early in case of big data. You try to store and capture as much as information as you can, and then you could build a solution later point of time. But the inverse is not possible. Big data is not only about Hadoop. There are many solutions as you can see in the next slides. Alright, so there are quite many questions. I'll just go through them after this slide. This slide shows that there is a huge demand in the industry. Gartner and Forbes is still in 2015's case study. They have still pointed to big data as one of the hot technologies, and there is a huge uh, gap of demand and supply. That is why the salaries in big data domain are higher than the Java kind of people. And this is the traditional big data solution. Sorry, not this. Okay. Now let me have a look at your questions. Now Rajesh's question is, who frames the problem statement for the organization? Big data problem statement. That is okay. So generally there are people who, I mean, there's not a single person. I have been mainly I have worked in organization where there is no single person who forms the problem statement. All right. Say for example, when I joined in Mobi, the assignment which I was given was very vague. The assignment was that our users do not know us. We show ads to our users inside the game they are playing. So when you play the game in Android or anywhere, most likely the ad you see is from InMobi. All right. Now nobody knows about InMobi. So my role was to figure out a way to build that kind of thing. So instead of showing ad, I started showing recommendation to the end user. And that's what built the perception of the company, that, that that's what build the engagement between InMobi and the end user. So from the very strategic point of view, it was a very vague problem statement. To refine it, to convert it into executable thing, it's a role of many people in an organization. All right. Now, Kazri's next question is: suppose I want to analyze chats for sentiment analysis. My first step, I want to process, read them, structure them, store them, all parallel chats real time. Only afterwards I will run the data analysis. So the first step is the big part of the solution. That is correct. That is correct. So first step is the biggest part of the game. But before you take the plunge into first step, you should know what is your long-term goal. And that long-term goal will dictate whether you will go for Hadoop or any other solution. Naveen's question is, let me make my window bigger. How can I make my window bigger? Okay. Okay, Naveen's question is that one of my responsibilities to hone channel partners to develop skill sets on analytics, as they are going to get more opportunities in this market. If you could tell me who in a company takes a decision on outsourcing the big data services offshore or as near shore analytics partner. So generally this kind of decision is taken by two kind of people in organization. One is CIOs of a company, because this is the most important thing, and every CIO as of today is talking about big data analytics. So it's the CIO mostly, or the strategic group. Generally every CIO in an organization have something called a strategy group. So you should actually either talk to CIO or any of the member of the strategic group. All right, not CFO, not operations guy, but CIO or the strategy guys. Now, next question from Naveen is: does the traditional BI product like Tableau or MicroStrategy can solve big data issues? So most of them do not and cannot. Okay, because when we talk about big data, it's difficult, but they are used in conjunction. It's not that they are obsolete. For example, when we will be doing an exercise on sentiment analysis, in that the whole churning of the data will happen on Hadoop, while presenting the data to the end user or to the management could happen using any of these BI tools. Right? Mostly, big data processing, objective of big data processing is converting the big data into meaningful, smaller information. Okay. Next question from Naveen is: why companies prefer to license and purchase the big data software products? Why can they not go for services like service provider like Infosys or TCS etc? Maybe last question, don't worry. So why companies prefer to license and purchase big data software products? Why can they not? So they want to build just like every company want to build a BI team. Similarly, every company wants to build the capability also. All right. And I would say that companies should build their own capability rather than, because data is not something I would like to outsource to my partners. It becomes a very big deal. to transfer all the data to my service provider. All right. Therefore, if I am in the shoes of a very large organization, I will say that data is my key strategy, and I will not just give it to anybody. Okay, even if there is a non-disclosure agreement. So I would buy software products specifically if I'm interested in the information. But there are companies who give out their big data solutions to the end user. Harish's question is, can you give some example this is used in high frequency trading or stock market trading? Good, good. So in high frequency trading, I mean, you will be surprised to know that what does D-Sha do? In 2002, we were actually doing a high frequency trading, and we were actually D-Sha is the largest hedge fund. It's a finance company, largest hedge fund of the world. All right, and we had been doing all of this high frequency tradings using big data solutions. We had our own AI teams who basically built these neural networks, and that neural networks took decisions really, really fast. Okay, the beauty of neural networks or beauty of AI is that it learns, and once it has learned, the decision making is fairly faster. Okay, so we had been using it for quite some time. I mean, that's the biggest use case I can tell you right now, which I've seen with my own eyes. Okay. We used to analyze a lot of data from Bloomberg. We used to buy the lot of data from Bloomberg, all kinds of data. Ram's question is that when not to go for Hadoop. Okay, so first I'll explain to you why not to go for big data sometimes. Sometimes your data is smaller, and sometimes your data is fairly structured, and you do not have you have a clarity of the growth, that this is not going to grow beyond few terabytes data and will be able to handle using MySQL or your own relational database. In those cases, you should not be going for any big data solution. All right, but there are cases. So that is one. And we will talk about when to use Hadoop, when to use Cassandra, when to use this, when to use that in later point of time. All right, Ram? All right, what is the critical skill required for big data? That is Ravindra's question. So I would say for this particular session, the big data and Hadoop, there are three basic skills required. One, you should know a little bit about uh, control structures in any programming language. You should know what's a for loop, what's a while loop, what's a variable, what's an array. You should know these kind of things. Okay. And you should be ready to try out things. You should be ready to learn a little bit new kind of language. Okay. Second is you should know what is a database, what is an SQL query, and what is a join in SQL query, what is order by, group by, and that those kind of information. Third is you should be okay to try the command line on Unix or on your Windows. All right. So those are the critical skills required for this particular course. But since big data is a big domain, there are many kind of domains, many kind of positions. You might not, you may not require programming skills at all. All right. So let's take a break for 10 minutes and come back after 10 minutes. Then I'll answer your questions. We have got brilliant questions in this session. All right. Hi guys, I'm back. Can you hear me? All right. So we were discussing your questions. Now Rajesh's question is, looking at the current slide, how can one aspirant get a big data opportunity given that not many of us have any development experience in big data projects? So first, I'll try to rephrase Rajesh's question. His question is that how can we get the opportunity? Why would people hire somebody who is a fresher in the big data domain? Right? Now, good part about big data domain is it's not too much different from what we have learned so far. There are few technology which add on to the existing technology. Okay. If you are not aware of what is big databases, it does not make much sense to talk about few of the components such as Hive and Pig Latin. Okay, so your existing experience matters fairly well. Second, most of the aspirants in the big data domain or most of the people are in the big data domain are freshers. The technology is fairly new. The technology stack, the Hadoop and stuff, is fairly new, so it's actually very difficult to get the get the experienced people on board. Okay, so most of the recruiters have realized that it is okay to go for a fresher in this domain but have somebody who has some industry experience. All right, so that is how it is mostly. Now there is Naveen's question which says mu sigma per se got it. Are there anything we can assure clients on big data security and compliance saying we do not spy on the data? Okay. Now, Naveen's question is that it's for both the people on both the sides. So if you are a company X and you want to outsource your data, because you are outsourcing your big data solution to somebody, so how can you ensure that the other company is not, how can you trust the other company? Okay. First, you sign a non-disclosure agreement with the other company who you are outsourcing your data to or big data problem to. Second, you basically remove the people specific information. Okay. You need to remove all the data and basically you generate a different set of IDs for each user which you pass on there. Okay, there is a good term for this. It's called making the data anonymous to the end user. Okay, so those kind of things could be done, but to do even this kind of operation of you hiding the user information before handing over to some company, it requires a decent amount of capability in terms of hardware and the people. Now, Palani's question is, can we use big data in manufacturing domain? Yes, you can use big data in manufacturing domain. In manufacturing domain, the basically even if you get, there are lots of things you could do in the manufacturing domain. Maintaining the health of your machinery and keeping track of the production line with every day details about every machinery along with the along with other information like climatic conditions and everything. If you combine most of this data together, you can come up with really good insights which you can utilize in order to improve the production. Okay, there are many use case actually in the manufacturing domain. Santana's question is that can you repeat when not to use big data? When you are happy with your solution on a single computer, there is no need to go for big data. As simple as that. Second, in case you desperately want a strong consistency and transaction support on your data, don't go for big data solutions. Are you guys able to hear me? All right, because somebody was complaining that they are not able to hear me. Palani, maybe you let me type to him because, uh, yeah. Now, all right, all right. So I think I have. Was I able to answer your questions? Great. All right. Any other questions to me? Brilliant set of questions. Really appreciate your questions. Okay. Now, all right. Should I continue now? Great. Now, there are many solutions in big data domain, and one is Apache Hadoop, second is Spark, then Cassandra, then MongoDB, and Google Compute Engine. All right. Let me describe you in brief. So, Apache Hadoop is probably the most complete solution. Okay, it has everything in it. It has a file system, it has a database, it has a compute engine. Okay, so basically whenever whatever you have to do with data, you start with storing data into the files, or you might store the data into a tabular format or in any other format. Third, you might want to do some sort of processing on top of this data. Fourth, you might want to generate all kinds of insights on top of this data. So all of that is actually there in Hadoop. Second is Spark, Apache Spark. So Spark is only a compute engine. It doesn't provide you a database. It doesn't provide you a file system. It's a beautiful, really fast compute engine. Also, it comes with a machine learning library. Spark comes with machine learning library the way Hadoop comes with, and it's quite useful. Now there is something called Cassandra. Cassandra is sort of a database. Okay, we call it NoSQL database. So it's sort of a database where you store the data in the form of a tabular table. Okay, and it's fairly fast, and it runs on multiple computers simultaneously. Now, third one in the game is MongoDB. Similar to Cassandra, MongoDB is also a database which runs parallelly on multiple computers to provide you the ability to store and process humongous data. Okay, here the data is in the form of objects. Now, fifth one is your Google Compute Engine. In Google Compute Engine, there's everything. There's a hardware as well as software. All right, and it's little costly. So these are the various solutions. And okay, so Malesh is asking for this to repeat. Okay, so don't worry, you have not missed anything. Okay, you anyway, this is getting recorded. You can go through the recordings, no worries. Okay, I do not want to, other people might not like it. All right. So you have not missed anything. You can just go through the recording, and that will be good. All right. Now, Palani's question is big data supports only text data, image data, object data? So big data is anything actually. It's not only text, image, or object. It's also well-structured data. It's also the well-structured data. All right. All right. Anybody else wants me to repeat this slide? If you want, like, just let me know because Malesh wants me to repeat. In case there are more people, I can repeat it. All right. All right. Green Plum DB is another solution for big data problem. It may be. I have not used Green Plum. Okay. Okay. I've not used Green Plum, and it may not. I'm not sure about it. But there are close to 150 NoSQL databases which run parallelly on multiple computers, meaning have distributed architecture and are able to support a humongous data. Okay, there are close to 150. Okay, all right. Okay, so I'll just yeah. So Malesh, no worries. Let me just repeat only the Spark part. That is fair enough. Okay, because probably it will be good for others also. So what is a Spark? A Spark is fairly fast compute engine on which if you want to get something computed, it computes on multiple computers simultaneously and is really fast because it utilizes memory to a very large extent. All right. Spark is just a compute engine. It does not provide you a storage. It doesn't provide you a NoSQL kind of database. It does not provide you anything other than computing. Though, from the computing point of view, it provides you a normal compute engine where you write your program, hand it over to Spark, and it runs parallelly. And it also provides you to an SQL kind of way to churn a lot of data. It also provides you a machine learning library which does a lot of computation on various data. Though Spark utilizes Hadoop for its data storage. All right. Isn't Google Compute Engine a virtual machine to run on Google Cloud? That is Kazri's question. Google Compute Engine is not like your normal cloud. No, it's not like a virtual machine, unlike AWS and other stuff. There you basically upload the data, write your logic in MapReduce and other similar system like Big Data Query which they have provided to churn the data. Alright? It's not really like a VM. It's more like a software interface. Alright, now going ahead. Alright, so everybody with me? Now, Santana's question is similar to how Spark uses Hadoop, will any other big data solution uses MongoDB? Yeah, so most of these systems have been made to work well together. Okay, so for example, for example, there are drivers, JDBC drivers with which you can connect to MongoDB and get your output work done. Okay, so and then other systems can communicate with MongoDB. Mongo Hadoop, MongoDB and Hadoop can work together using Mongo Hadoop. You should have a look at that grid project, that will be useful. And there is a video on how Mongo Hadoop and MongoDB can be communicated, can be connected together. All right, so good. All right, so moving on to Hadoop now. So long back, when there is a person called Dog Cutting. He was working at Yahoo, and in his free time, he and Mike Caffarella were trying to build a search engine called Nudge. And when they were building that search engine, they realized that it doesn't make sense to build the search engine because storing an unstructured data is impossible using existing file system solutions. And luckily, Google released the paper describing how they built Google file system at the same time. So they built Google file system as well as Google MapReduce and Google Bigtable. Based on these three components, Dog Cutting, Mike Caffarella, and other people who joined them, they wrote the product parallel to these three, and that was called Hadoop from the beginning. So Google file system was implemented as a, HDFS, Hadoop Distributed File System, and Google MapReduce became the Hadoop MapReduce, and Bigtable became NoSQL HBase. Okay, Bigtable became the HBase database. Okay, now that's how Hadoop was born. The good part about Hadoop, why it became popular, probably was the Apache licensing. Apache licensing is really brilliant licensing. It allows you to use any product, even in organization. Even you can sell your product which bundles Apache Apache license products, such as say you are selling your product and your product requires to be run on a web server. So you can actually bundle say Tomcat along with your product. That is the beauty of Apache license. So probably the single important thing they did was made the Hadoop as Apache license. And after they made this as Apache license, it became very popular. Right? People were able to learn it faster, people were able to train other people faster, and people were able to contribute to it. People were able to use in organizations without a fear of getting sued from someone. People, the developers were got a free hand of trying it out. That is the power of Apache license. Okay. Power, the third line F, power, powerful, popular, and supported. All these three comes from the point number E, which is Apache license. Now, after a point of time, Hadoop mostly became an umbrella term for various kinds of products. It's no longer a single one. So it has many sub-projects as of today. And all of these sub-projects have these common features. They are All of these sub-projects are for reliable, scalable, and distributed computing. Reliable as in case one node goes down. Distributed means your software runs on multiple computers. Reliable as in case something wrong happens, data is not lost. There is always some sort of backup. Second, scalable. Today you require few computers. Tomorrow, if you require more computers, you can quickly add without worrying too much. Okay, that is scalable. You don't have to shut down and clean it up and do all sorts of juggling. You just plug in a new machine, attach it to the existing cluster, and the load balancing happens. So that is scalable. So all the components which lie under the umbrella of Hadoop have these three properties: distributed, reliable, and scalable. And Hadoop is mostly written in Java. Hadoop is mostly written in Java except for Zookeeper, which is not written in C. Rest of the components are written in Java. And why is it so? Because the overall objective of basic components such as HDFS and the compute engine, their overall objective was to run universally. And by virtue of being in Java, everybody was able to quickly adopt Hadoop everywhere. As of today, Google runs Hadoop on their compute engine. Amazon runs Hadoop on their AWS. Microsoft provides HD Insights, which is basically Hadoop on their Azure network, and so on. And that's probably because it is Apache license, plus it is written in Java. All right. So this is the basic point of view. Probably this diagram will make it far more clear to you what exactly is Hadoop. Okay. So before we jump into the whole ecosystem, today we are going to discuss the base of all of this. The base of the whole ecosystem is Hadoop distributed file system. A file system which runs on multiple computers. It runs on multiple computers, providing you thousands of petabytes or exabytes of storage. And on the Hadoop distributed file system, the whole ecosystem stands. There is no head-on competitor of HDFS as of today. There are databases, but they are not competitor of the file system as of today. So we have got HDFS, and all the components actually use HDFS. So that's why we will like to jump into HDFS, and this is a fairly technical game now. From this point onwards, before we come back, before we come back, we'll be detailing on how exactly this component works. Okay, fairly technical, but I'm sure you will be able to understand it. I'll try my best to make it so simple, to keep it simple that you can understand, even if you have never built or architected any of similar systems. Okay, so do not worry, be with me, and I'll try to explain how is this built. This is an important reason why I want to explain you the architecture of HDFS. All right. So let's jump in. Let me ask you a very simple question before I start. The simple question is, if you have to store 100 terabyte of data, how would you store it? Imagine this. In your organization, in your office, there are 400 people. All of you decided that let's build a central storage where we can store the movies. Okay, here I'm not talking about breaching the breaching the copyright. All I'm saying is that just imagine this, for the reason of just I'm trying to make up a problem. So, in an organization, you are 400 people. You decided that we occasionally, all of us have to watch movies, and let's build a central system with 100 terabyte of storage where all of us will store our movies and all of us can watch our movies from that central place. Okay. So, if you are given this task, how would you build this kind of storage? Yeah, question is to you this time. Yep. Shesha says that we will use backup hardware softwares. Okay, go ahead. Amit says store the files on a disk and then expose the index via a service. Excellent, excellent. All right, good. Now Rajesh's suggestion is I'll have 100 computers in a distributed network, and with each having 1 terabyte hard disk and 8 GB RAM, 1 gigahertz processor. Very excellent, very good. 10 TB of data on 10 machines. Good, good. Go ahead, go ahead. Anybody else? Yeah, anything that comes to your mind. Basically, you're building a movie storage for your maybe apartment community, your hostel, or your organization, where all these people can store the movies in a central place and then they can watch it. They can watch any movies out from all the people. Okay, so we have four questions as of now, four answers. Go ahead, I'm waiting for your answers. Anything that comes to your mind. Trust me, it is going to be okay. Anything that comes to your mind when we talk about this. My overall objective is here convince you, I mean, taking you into into basically making you design the HDFS actually. That's what I'm trying to do here. Kunal says build a cluster of nodes, share data with them. Excellent. Harish says that use MongoDB clusters. Okay. And if you're using MongoDB clusters, how are you going to provide me data in the file system? Everybody, all of my users are supposed to have MongoDB client, right? And before watching a movie, they'll use a MongoDB client and download this data, this binary data as movie, and then they'll start watching, right? They can't just point their VLC to start playing the movie from the network. But that's a good answer. Jairam says that can use unutilized storage. Okay. Rajesh says 100 computers will also have mirror of each other sharing 1 terabyte hard disk failover. Excellent, excellent. Two things. One, a central space to store movies. Two, this is I'm reading Siddharth's answer. Two things. One, a central storage to store movies. Second, a network connectivity that enables every system to talk to each other. Good, good. All right. So, perfect. Very great answers from you guys. Here is the design which probably some of you have talked, Rajesh and Sarju and other people, and maybe Kunal. All right. Now let's imagine this. We bought 100 terabyte of drives, made 100 subfolders. Say what you did was you put these 101 terabyte drives on say 50 computers, meaning two hard disks on each. And or maybe let's just for simplicity reason we just bought 100 computers, and on each of these 100 computers we installed one hard disk. All right. And on and to be a little bit on a safer side, we on each computer we also build a backup of each hard drive, which means 200 terabyte of the storage. Right. Now we have got 100 hard drives in the network. To make it accessible to the user, what we are going to do is we are going to mount, or in Windows way, we are going to map these hard drives onto a single folder so that anybody can come from the network and start accessing these folders. Drive 1, drive 2, drive 3, drive 4, and drive 10. Right? Now, there'll be these many folders and you will be storing movies in those. Do you see any problems with this approach? Do you see any problems at all with this approach? Is this approach clear? So we connected these hard drives into the network by the way of connecting these computers, and then we mapped these drives to one folder each. Now, do you see a problem in this architecture? Anyone? Synchronization. Synchronization, be a little bit more specific. But you're on the very right track. Just I need more description from you. That was Rajay. That was Santana. Rajesh is saying perhaps one movie at a time. Okay. Meaning, okay. So Rajesh is saying perhaps one movie at a time. Meaning people will be able to watch only one movie at a time. Or Harish is saying retrieval speed will be slow. Very good. Very good. Reason being, we will go into the details. You think about what does it mean by retrieval speed going to be slow. Shesha is saying, yes, if one goes off, the data will get lost. That is true. Sarju is saying that mount points are increasing linearly. More and more nodes are coming in. We are keeping mount points more and more. That is correct. Kunal is saying file system should have to handle the deep subfolder system. That is correct. So if there is a data, half of the data we want to store in one folder and another one into another folder, that will be a little difficult game here. Rajesh is saying only the movies that are mounted on the drives Okay, maybe it's a continue. Okay, only the movies that are mounted on the drives. Oh, I did not get your point. Maybe you are typing right now. Network problem. Thank you, Pilani. Because yeah, that will be a network issues. That Baswaraj is also having the same point. No redundancy. That is correct. That was case of. Anybody else? Anybody else see the problems? Although all of you have actually covered what I wanted to say. Great. So first problem which everybody of you raised is the backups and the failover. In case one of the hard disk goes down, what happens? Is there our data available somewhere else which will come to the life immediately? Second, how would you distribute the data uniformly? How exactly? Meaning you have got a big file, say 30 GB, and okay, let me take a step back. Here we said drive 1, drive 2, drive 3, drive 4. You came up with a scheme that let's store all the movies starting with A on drive 1 and drive 2, and all the movies starting with B on drive 3 and drive 4, and so on. Now there are multiple problems associated with this. First, what if there are too many movies from starting with A, but there are only few movies starting with B, which means some of the drives are fairly free, while some of drives we are not able to fit in this movies. Okay, therefore this mapping, this indexing has to be built, saying these movies are stored on this and this and this. But still there would be a problem saying, say we want to store a new movie which is 20 GB Blu-ray. Okay, but there is only 19 GB available on a computer, while there are other computers also empty. So you will go to other computers, store your hard disk, but this 19 GB you were not able to utilize. Okay, so therefore in a single word, we were unable to store the data uniformly onto this cluster. Third one is this best value for money? You are buying these costly hardware in your organization. You might already be having the similar hardware lying around, or smaller hardware. There'll be 1 GB hard disk, 2 GB, 3 GB, 10 GB, and so on. Are you utilizing all of that hardware? Now, what about increasing accessibility? Some of you have actually pointed onto this. This is really, really important point which all of us miss. Specifically, all of us who come from a background of handling the data through RAID. We miss this point. Imagine this. Let's take a step back. Every Friday, a new movie is going to get released, and by Saturday, somebody is going to upload that movie onto this cluster. Now, everybody wants to watch that movie, the movie which has recently come. When everybody wants to watch that movie, and that movie is, say, stored on the first drive, now everybody is going to access that first drive, and that drive is going to die. And therefore this schema is not accessible enough. While one computer will be bogged down by so many requests and other computers are fairly free, therefore this system what we just discussed is not meeting the requirements of accessibility. And the other problem is scaling out, meaning today we need 100 terabytes, tomorrow we might need 150 or 130, and so on. Our system, whatever system we built, Is it scalable enough? Of course not. Kunal's point is, can't we design the system so that it treats all the hard disks as continuous space? That's exactly what HDFS has tried to build. Okay? That's exactly what HDFS has tried to build. All right? Now, then the solution is using HDFS and it'll solve all the challenges. Now, our next question is, how does HDFS work? How does HDFS make it possible to handle all the issues which have been raised in the previous slide? All right. Now, basically, I'll just go in a very, very simple manner. We'll go into more details into second session onwards. So, Hadoop distributed file system is nothing but a bunch of computers connected together. And these bunch of computers are of two kinds. There is one guy called master node or admin node or name node. That's a singular guy. And there are other guys, other nodes in the network which we call data nodes. So in an HDFS system, you have got one admin node, other data nodes. Okay. So admin node, as some of you suggested, why don't we build a service which shows the index, right? Some of you, I forgot the name, suggested that let's create an index. That's the exactly what admin node does. Admin node does sort of an accounting that this file exists on this data node, this file exists on that data node, and so on. So this is a huge big mapping of which file is where, right? When user comes to admin node, it can look up quickly that where is this file, all right? So data node is something which actually stores the real data, the data which is inside the file, while admin node stores the information such as the directory name, file size, file attribute, and so on. So the metadata onto your data is stored onto admin node. Okay. Now let's go a step further. What happens inside data node? Data nodes store the actual data, but in the form of blocks. Instead of storing the whole file, the way HDFS works is that it stores the data in blocks. The default size, the one Hadoop provides is 64 MB block size, while for most of the installations like Hortonworks or Cloudera, it's 128 MB. So a file is split into the chunks of 128 MB, and then these chunks are stored on data nodes. And the chunks, the blocks are distributed onto multiple computers so that a file exists on multiple computers rather than on a single computer. All right. Now, this division of file into blocks suddenly changed the whole game. Now you can fit bigger size file into a smaller space available. It leaves less space unutilized. Okay, it leaves less. It doesn't. It makes the full utilization of space. Second, we will talk about why do these data nodes talk to each other and transfer the data. If there are blocks, it optimizes the transfer of the data. Okay. And also, since we are going to Since we are going to store a single file into blocks and these blocks are stored on multiple computers, if lots of people are asking for this file, they will be using multiple computer and instead of a single one, right? Now, a little more detailing. Each block is copied onto other nodes, and there are total number of 3 copies by default. We can change number of copies as well as the block size, but to avoid the confusion in the discussion, let's just keep it as 3 for time being. So each block is copied onto multiple nodes, and these copies are called replication factor. Okay, so each block is replicated to multiple computers, and this replication is called replication factor. By default it's 3, so that in case one data node goes down, the data does not get lost, because every block that got lost because of one data node going down, there are 2 copies of the same block which got lost are still available in the network. And the moment it is realized that one data node has gone down, and due to which our replication factor has come down from 3 to 2, data nodes are informed to start replicating those blocks so that their replication factor of each block would again come back to 3. Okay, so a data node goes down, replication factor got decreased because one block got lost out of 3 copies. So now there are only 2 copies. Now, data nodes will be informed to start copying the data, making one more copy of all the blocks that got lost, so that the replication factor is again built in and is ready to handle further outage. It's ready to handle the further outage of any of the systems. Okay, and this way your file system remains heavily resilient towards the failure of any of the nodes, and that is why it is heavily reliable. All right, now this replication factor, if you increase this replication factor, the blocks are going to be, each block is going to be on multiple computers. Okay, if you have 100 nodes and you copied each block 100 times, your file is going to be at 100 places in the network, right? Now, when a user comes to read the data, he'll be reading from all the data nodes across the cluster instead of only one node. Okay, so it'll read first block from one node, second block from another, third block from another, and the user can do it all parallelly. And hence your speed suddenly becomes really fast. All right, now let me take up your questions, or just give me 2 more minutes, because I'm sure your questions are going to get answered in those 2 minutes. Secondly, we talked about admin node, that admin node is the index, and we talked about data nodes. So the first impression which we built is that node or name node we call it, name node is going to be bottleneck, because user is coming and name node is reading data from data node and giving back to the user. So don't have that impression. This is not the way it works. The real design is like this. User uses a client or a command line or a driver to access the data. And this client or driver first goes to the name node and asks, hey, do you know where is this particular file? And this name node tells the user that go to data node 1, data node 2, and data node 3 and get these blocks from there. And the client will directly talk to data nodes instead of reading through the name node. Because if client start asking name node for the data, what will happen is the name node will choke and client will get a very bad performance. All right, because if everything is going through the name node, then the whole purpose of distributed computing is fairly lost. Okay, now second question is you must be asking by now is what about the name node failure? What if name node goes down? What do we do? So name node comes with now high availability. Okay. As soon as name node goes down, there are backup waiting for taking its place, and name node can start functioning perfectly fine. All right. So there for name node, there's always a backup which is in passive mode. The moment name node goes down, it comes to the life immediately. Okay. So Zookeeper can be configured to give the high availability for the name node. But don't worry about Zookeeper. I don't want to talk about it right now. All you need to understand is, as of today, you can always have name node in high availability, but there at a time there will be only one name node talking to the client. And why is it so? Why don't we have multiple name nodes just like data nodes? The reason is consistency. HDFS tries to have it very consistent. So in case imagine this, there are two servers containing running name node. One name node, both of them are accepting the write request from the users. Now there are humongous chances of conflict. All right. Now let's answer your questions. Shesha's question is when we make machine, say machine 2 as data node, will it be still be alone standalone machine at the same time? All right. So that's a very genuine question. So in the first diagram, look at this. When we say admin node, data node or name node, admin node or data node, what does it mean? They are essentially a process which is running on these machines. So data node is nothing but a process which is running and listening on a particular port on these machines. So on data node is basically it's not a physical some sort of a computer which bought. It's basically a software. It's basically a process running on a particular port. Same case is with admin node. And therefore you can still run local processes just because data node is one Ubuntu server and admin node is another Ubuntu server and so on. You could still keep on using the way you had been using a data node. Okay. So it can act like a standalone as well as the network system. Okay. Now, can we control redundancy according to number of requests dynamically? As of today, no. So question, let me rephrase Kesav's question. Can we have this model automatic detection at HDFS level that the moment that lots of people are trying to watch a movie, it automatically start rebalancing, start increasing the replication factor. Imagine this, that today is Amitabh Bachchan's birthday or today is some actor's birthday. Now, there are high chances that the people are going to watch those movies more. Now, now, The moment, so his question is, the moment we realize that there is a system realizes that there are a lot of people trying to access this movie, it automatically increases its replication factor. So right now it's not there, but you can build such a system as of today also. Okay. Okay. What happens if one of the machines not available? I'm hoping that this question got answered, Sukesh. If not, I can repeat it. All right, no worries. So Ravindra says that is it similar to torrenting? The idea is heavily inspired by torrenting. Okay, breaking down files into blocks and all right. Okay, default 3 would means at least 4 machines. No, default 3 means at least 3 machines. All right, that was Sesha's question. Thank you for clarifying this. Next question from Sesha is, when we are switching between read, will it not reduce the read speed? Not really, it will actually make it faster. Because when you are reading a file, it is completely up to the client how it reads the data. Does it want to read it sequentially? First, let's finish reading first two blocks, then we'll read another block and so on. Or it wants to read all of it together. Okay? So it will not really, you know, it'll not really hurt too much. Okay, Sesha's next question is, where is the client or the client or driver is generally, it can be on the remote machines on which the processes are not there. Okay, but client can be informed that your master exists on a remote machine. Okay, client is generally, the client comes along with the Hadoop itself. Okay, but you can install client without having to install DataNode or NameNode services. Amit's question is a node analogous to an index and isn't a single source of failure? That is correct. So, so node which we are talking, basically you're saying about name node. So yes, so name node has got a backup as I said telling you, and it's in a HA mode, highly available. It can be configured to be highly available, meaning the moment name node goes down, the another name node which was in the backup mode comes to the life quickly. Rajesh's question is, I believe then name nodes will have superior configuration than data node. That is correct. So the index, the way name node stores the index in memory, and this memory is supported by the file system. Meaning that the if you want to store too many files, probably you will have to increase the RAM of the name node. Name node is heavily RAM intensive uh, machine, okay, and a little high end. While data nodes are fairly low end, and it doesn't, and it handles it very gracefully. All right. Kunal's question is, wouldn't exposing data nodes to the client have security risk? That was the reason why we had name node to be abstracted away, to abstract away the backend nodes. Not really, not really. So the design is not Here, NameNode is not abstracting the data nodes, first of all. NameNode is just acting as an index. That's all. Okay? It's not providing abstraction layer. Had it been providing abstraction layer, then NameNode will read data on your behalf from data node and then give it to you. That means NameNode will become the bottleneck. So NameNode does not proxy you. Okay. Second, your concern is correct. There are security risks, meaning if a client connects to HDFS and if there is no authentication, it can access any data, right? And it can access the data from the data nodes. But the good part is most of this communication happen over SSH, over TCP/IP, which is heavily secured. So you establish the trust between name node and data nodes so that they can communicate with each other. Okay, before you set up a cluster, you establish this by the way of using SSH keys or some other mechanism. You establish the trust so that a new node, which is a foreign node which knows nothing about name node or data node, cannot steal the data. All right, very good question. Rajesh's question is, what if the size of individual data node differ? Yeah. So the size of individual node can differ. It doesn't matter. So one of the data node can have 100 GB, other can have few hundred terabytes, and other one can have few petabytes of storage. Although it's not a good practice to have petabytes of storage on one node, generally on each data node we try to keep close to say 200 GB data. Otherwise, the read speeds will hit you really, really bad. All right. So the size of 64 MB or 128 MB is irrespective of what is the data node size. Okay. It is based on how much do you want. While you are storing a file, you can customize saying that this file should be stored with these many block sizes. Am I able to answer your question? All right. Now, Kesav's question is there something like P2B processing or distribute? Yes. So the whole idea, it doesn't stop here. When you will read MapReduce, you will understand this distribution of data made it possible that we could run computing on so many machines parallelly. Data node 1 will be running the processing, the data node 2 will be running the processing, so that the data is not being transferred before getting processed. Okay, so instead of sending the data to the code, we are sending code to the data. Okay, we write our logic, send it to each of the data nodes which get executed over there. Okay, and you get the output. So all of these machines will be doing computation as well for you. Okay, we'll talk about it when we talk about MapReduce in the next session. But good point, very excellent point. So Casey's question is, if there is an update to some data which is replicated, copied three nodes, assuming only one of the update is complete, when a new request comes in, how does admin node handle it? If there is an update to some data which is replicated, mhm, assuming only one of the update is complete when a new request comes in, how does a name node admin node handle it. Okay, so every update, so most of the Hadoop file system is write ahead system, meaning you do not edit the file. Instead, you create new set of blocks and delete the old set of blocks. Okay, so if you are altering a file, a new set of blocks will be created. Okay, and the old set of blocks will be destroyed, and the replication will happen just like as if it's a new file. All right, now Sarju's question is, what happens if three machines simultaneously go down which has a replica and whose replication factor is 3, and what are the chances and recommended value? Good, very good question. So Sarju's question is that there are chances that all of the nodes containing your the copies of a block, they all went down, which means one block is gone and hence the other blocks are useless. Okay, if it's a data and it's useful data, if one piece of the whole file is lost, the whole file is lost, right? Therefore it's generally strongly recommended that you have two data centers at two different geography. Why would it happen that all of these nodes go down? There could be fire in this data center, right? Because of which it is always recommended to have two different data centers. Okay. And other part is when you are storing a file onto HDFS, it makes sure that first block is very near to you and second and one block is very very far from you. So if you have a computer sitting in another data center, there are chances that your copies of all the blocks are available there. All right. Now Jabrikasi's question is, do name node and secondary name node work in the same way, and is both need to be having same hardware configuration? So yes, that is correct. So name node and secondary name node work in the same network. Okay, they are exactly mirror images, and all of these data nodes are informed about name node as well as secondary name node. So every change they report back to name node is also reported to secondary name node. Yes. So Brahmaji, I will be sharing the full session file, the recording as well as the presentation. Nothing to worry. Okay. So Baswaraj's question is, how will we ensure that all blocks are in different places? So this is something interesting. So when you are setting up your cluster, you inform Hadoop about the architecture of your nodes, and you inform that this is how my network is laid out, and based on that Hadoop will figure out which one is the farthest node from you. Okay, and accordingly it'll make sure that one of the blocks actually go to the farthest node, so that in case of emergency there will be at least farthest node will be safe. Okay, we'll talk about locality optimization in session number 4. All right, so any questions on this? Same diagram with another set of blocks. We have name node which contains all the metadata. Then there are data nodes which contain blocks. Because a client is coming and reading directly from the data nodes after knowing about data nodes from name node. All right. Similarly, this is the anatomy of the file write. The client came in, used the distributed file system, and asked name node that can I create this file? NameNode says yes, definitely, sure, but I'm making an entry saying that you are going to write this file. Go to these nodes and write your data, and once you are done with writing data, come back to me and I'll confirm. This is the psychology of the whole game. And when you write to one of the data nodes, the data gets copied to other data nodes automatically. And this copying happen between the data nodes. It doesn't happen like the file first came to the block first came to name node and then went to another data node. All right. Similarly is the file read. So, okay. File read is in the same manner. You go to name node. Name node gives you the block locations, and then you go to the data nodes and read the data. Okay. Let me talk a little bit. Okay. Yes, you'll be able to. It'll take me around 3 to 4 hours to upload this video, and I'll send you by morning. Okay. All right. So since I have taken wasted 10-15 minutes earlier, so I'll have to actually go for 10 more minutes. Okay. And I'm extremely sorry about this slip. Okay. So yeah, because session got started 5 minutes late and I took 10 minutes more break, so I might have to take 10 more minutes. All right. So bear with me. So this okay, this diagram shows various kinds of metadata, and metadata is always in the memory and kept in the disk as well. And what does it contain? The metadata contains list of files, name of the files, and what are the blocks for each files, and what are the copies of each block, and where all the node, which all data node contains which blocks. So this is the data kept and maintained by NameNode. Now let's talk about the whole ecosystem. Probably this diagram will do a better justice. All right. So we have HDFS file system, on top of which there are tools like Yarn. Yarn is a resource manager which makes it possible to run any logic. It makes it possible to run any logic on all the computers in your network parallelly. Okay, and and MapReduce makes it possible to run your program in terms of map and reduces using Yarn. Okay, using Yarn directly is not possible for an end user because it's fairly complex and more powerful. While MapReduce is just map and reduce paradigm where you write map code, reduce code, hand it over to MapReduce, and it runs it. Okay, and Yarn on top of Yarn, there is something called Spark also. Spark is a compute engine, and this compute engine can run on your Hadoop cluster, using your Hadoop cluster to do all sorts of computation. Okay, Yarn makes it possible to take the code to the data rather than bringing data to the code. All right. Now there's something called HBase. If you have to store the data in the form of 1 billion rows by 1 billion column and you want to handle it, then HBase is your friend. Okay, HBase is called NoSQL database because NoSQL is another term for databases which run in a distributed fashion. Okay, so HBase utilizes HDFS and Yarn in order to do the computation and storage. All right, the on top of these components lie Hive. Now, for every logic, small logic, I want to order my data, I want to filter my data. You don't want to keep writing the code in terms of MapReduce. Therefore, tools like Hive make it possible that you write in SQL, it will internally convert into MapReduce, run it on Yarn, and give back you the results. That is the role of Hive. Okay, Hive can read data from HBase, from file system, and churn the data using MapReduce and yarn for you. Okay, and it has become really powerful. The latest update is the update which got released recently provide makes it really brilliant solution for analytics. Now there's something called pig Latin. The few researchers realized that SQL was not meant to be for distributed computing, meaning Hive did not do justice in lot of cases. Hive did not provide enough power. That's why few researchers said and built Pig Latin. Pig Latin is similar to SQL, provides more granular control over your data. Okay, you can fairly assume that Pig Latin is more or less similar to SQL. Pig Latin provides you join. Pig Latin provides you where clause, filter clause, and then it also provides you order by and other stuff. Okay, and it's actually very beautiful language. Then there is something called Mahat. As I gave you an example, quick example of recommendation, that was just one program, one algorithm from the Mahat's library. Okay, Mahat is a library of algorithms which do lot of churning for you. It does grouping automatically. It's a machine learning library which does a lot of work for you. Okay, it's a magician on top of all. So this is what it is. Now, when you are building, say, your recommendation engine, so HBase means Hadoop database. All right, that was Pelani's question. Now, Uzi is a workflow. So when you're building a complex project like recommendation engine, you will be having many steps. First, you will download data from somewhere. Okay, I missed out Flume and Scoop to import the flat files. Okay, in real time you might use Flume, or in case you are unstructured data such as Apache log can be pushed in real time onto HDFS, and it's really faster. And then there is something called Scoop. Scoop is good when you are trying to copy the data from relational databases onto Hadoop. All right. Now, let's take a case of recommendation. In case of recommendation, if you're building such a project, you will be having first step as you bring the data, download the data from various places, and push it into HDFS. Once that is done, you would like to clean this data up and form that three-column way: user ID, product ID, and rating. So that kind of data can be only prepared using Pig Latin or using Hive or using your MapReduce. And once that is done, you can then call Mahat. Now, as you can see, there are 10-20 steps. When you sit down to build a recommendation engine, you will realize that there are 10-20 steps in the whole process. Now, you cannot keep doing it every day. That is why we require something like Uzi, which is a framework and which is something like Apache Ant or Make, or you can think of it like Maven, where it can execute various tasks along with a scheduler where we can say keep executing it every day on this time. So that is Uzi for you. All right. So that's pretty much about Hadoop ecosystem. And in this session, in these 11 sessions, we will be dealing with all of these components, including Spark. Plus, we'll also cover Zookeeper because that is a very good thing to learn, and that is something which will anyway come into practice in real life. All right. So we'll talk about all of these components in details in these 11 sessions so that you gain the 100% confidence of building an end-to-end solution on top of Hadoop ecosystem. So this course is stitched towards end-to-end solution on Hadoop on a big data. Okay. Even like sentiment analysis would require all these steps. Now, of course, startups can afford Hadoop. Why not? Mine is a startup. I have 20 nodes running parallelly for Hadoop, on Hadoop. Okay. I've just bought some few servers at my home on which I do a little bit of research. So I was trying to answer Kesav's question where he says that can startups afford Hadoop? All right. So, of course, startups can afford Hadoop. You do not need to buy blade servers. A decent amount of computing machine is good enough. A 30,000, 40,000 machine is good enough. So if you bought four machines of that size is great enough. All right. Now, if you have any questions regarding Cloud Labs, what we have done is all of these components, what you see here, along with things like Python and R, we have installed on central server. You can connect to these central servers using SSH and start using any of these components. Also, you can open it in the browser. I'll show you quickly. This is how our, all right, network connectivity, because I'm right now we're busy here. That's why it's taking a little more time. It's coming up. So we have got a central systems, multiple machines, so that you can really feel that when we gave computing, when we ran our Hive, how did it run on multiple computers? Okay, you can experience that exactly the way we had a cluster at InMobi and Amazon. I've set up a similar cluster here so that you can get a feel of how does it happen in a big data organization. Okay, so that's Cloud Labs. And also, you don't have to install that heavy virtual machine onto your computer. It's up to you. We provide you the support for both. Okay, so this is a little bit of assignment for all of you. Those who have signed up for the course, those who have enrolled for the course, go through the LMS under your My Courses. In the session 1, you will see an installation document detailing you how to install virtual machine as well as detailing you how to connect to our Cloud Labs and start working on that. Second things to do for you is go through the quiz listed in the session 1 and answer it quickly. Okay, you can try as many times as you want, as many times you want, just that we record each session. Okay, each results will be recorded with us. And but you should try it out couple of times and try to be try to give answer correctly. There will be few questions related to yarn, but you can ignore that and finish it after the second session. Okay, you can skip those. All right. Now, those who have not signed up, they can sign up now. From second session is tomorrow. Tomorrow, as in 8th March. Okay, and you can continue this session. All right. and these are the prices in terms of in INR. This is, and in terms of USD, it is $302. Okay, so feel free to reach us at this number and this email ID. Okay, if you have any questions. So those who are interested in signing up for the course can sign up. All right. So thank you very much and see you tomorrow. All right. And you can enroll from our website. From here, you can just go to Hadoop and then you can enroll. Okay. Here you can enroll. This first one you can enroll for. All right. Any questions for me? All right. Great. Any questions for me? I'm happy that you really like the session. Thank you, Keshav. Thank, thank you, Basraj. Thank you, Sarju. And if you have already enrolled, you don't have to worry. Okay. If you want to continue the session from tomorrow onwards, you will have to sign up for the course. Okay. Thank you, Siddharth. I'm happy that you found the session wonderful. Okay. Thank you, Mohammed. I'm happy that you liked it. Thank you, Brahmaji. Thank you, Rajesh. I'm looking forward from tomorrow onwards. Thank you, Kazri. I'm happy that you found it helpful. Great. So feel free to, if you are you maintain a blog, generally you should put the highlights of today's session that will actually build a good reputation of your blog and put it on LinkedIn, and maybe you mention us on your blog. Okay, that will be, generally that is how few people do, that they write down the highlights of this session and then they link the PPT. This PPT will be shared with you. Okay, all right. Even if you do not maintain a blog, it will be a great idea to actually maintain a blog if you are into technology that gives a visibility to the world to know about you. Okay, great. Thank you, Malesh. I'm really happy that you found it knowledgeable. All right. So see you tomorrow then. Have a great day. Bye bye. Yeah, I'll send it as a PDF. PPT is not possible. I'm using Keynote. PPT is not possible, so I'll send it as PDF. That was Muhammad's question. All right. See you then. See you tomorrow. All right. Bye bye.